Okay, we are somehow in the final video of finishing the first chapter. Uh, you probably have noticed that I spent a little too much time on the first chapter. The reason is rather simple. First, many of you are new students, and going a little slow is probably helpful. And another reason is some of the material I covered are quite advanced. To be honest, they are actually way above the level of this course, or way above the level of any actuarial science course. Um, Somehow I was teaching this more as a mathematical course rather than a actuarial science course. So it may be challenging to some of you, and please don't get disencouraged from starting. Okay, even the materials are quite difficult because later on, you know, as you will see, once we get to the homework, to the exams, those are a lot easier than my lecture content. So it's okay to have a little trouble with the lecture videos, but please try those examples and homework from the textbook. Okay, you should have, let's say, a lot easier time, you know, with those. Okay, here I do have one example. I'd like to show you how to apply Panjer recursive formula to figure out the corresponding probabilities of the compound distribution S. So again, here, what we want to calculate is S. Usually the starting point is easy. The starting point is 0. Okay, 0, you can easily apply the probability generating function at 0. And we know this is lambda times theta minus 1. I write it down because, you know, we just proved this result. So here is a particular application. So I just need to plug in the values. Lambda is 2, theta is 0.2. So this is exponential negative 1.6. If you calculate, the probability is about 20%. Okay, so here I keep the value in decimal places. So I keep 4 decimal places, okay, because eventually this is a percentage. Okay, I need to apply Panjer's recursive formula. Okay, so if you forget, you can go back to the formula to take a look. Okay, so I first copy the general formula. A times fx 0. So now I'm doing summation from x to 1 to s. So obviously this s is this one, okay? This is small s, not big S. So here's a plus bx over s times fx s times fs. Here is s minus x. So for capitalize the letters, sometimes I will put a little cross, okay, horizontal crossbar to denote this is the capitalized letter. So this small s, well, in this case is 1, right? So, and for Poisson distribution, A is 0. Let me get a little bit more space down here. So I need, so let me get the pen. So A is 0, B equals lambda, here lambda is 2, okay? So because A is 0, so the first term is basically gone. So I can cross this out because A is 0, so it's 1 over 1, so it's gone. So A is 0, so I don't need to write this. B is 2, so this is 2, okay? In this particular application, we are looking at the value at 1. So this is summation from 1 to 1. So I have 2x, x is 1. So I have 2. Okay, so that's everything I have. So now I have fx at 1, f as 1 minus 1 is 0. Okay, now I need to know the probability of x at 1. So that is 1 minus theta times theta. And the fx0 is theta, so it's 0.2. So here is 0.2 times 0.8, so 0.16. So this is 2 times 0.16 times 0.2019. So basically, you will get a result 0.646. Okay. Let's move on to do 2. So now I have summation from 1 to 2. Okay. I have 2x divided by s. S now is 2, so it will be cancelled. So here is fx x fs, so it's 2 minus x. Okay. So I have, when x is 1, this is fx1 times fs1. Next, I have x is 2, then this is fs0. Okay, so the value I have is 0.16. The value down here is 0.0646 plus, okay, the next one is 1 minus theta squared times theta, right? So it times by another 0.08, so it's 0.1024, okay? No, it's not 1024, it's 0.128. So it's 0.128 times the probability of S equals 0, that is 0.2019. Okay, eventually you will get a result. Okay, if my computation is correct, this is about 0.06. Okay, please check. You know, my calculations are not always reliable. So check the result, but of course, you know, the main application is definitely correct. This theorem, it really looks close to the standard result of Poisson distribution, right? So when we have Poisson, we add them up, is another Poisson. And the intensity is nothing but the summation of all intensities. So here, a lot of things, you know, still stay true. The part that it needs a little study is the new PGF of S. So basically what we have is here. Each SI is in compound form. So let me, I should use a different index. So use J. So here let's call it Xij. Okay, I refers to the selection of S. Okay, what I have is I know Ni follows a Poisson distribution with intensity lambda I, and I know for each given I, Xij's are IID, and I know the probability generating function is Pi. Okay, so those are all the information I know. So now what I want to study is the sum of those SI. Okay, please keep in mind that now I know how many SIs I will be summing up. So it's small n. Okay, so it's not another random variable. So here you just need to apply the definition and do a little. So let's study. This term, I want to know this. Okay, then I apply definition. So it's T to S. From n to I to n, S here is Si. Okay. Because all those SIs are independent, so eventually they become product. And obviously that is the probability generating function of each one. And because it's in compound form and the primary distribution is Poisson, so I know this is exponential lambda I times each individual PGF minus 1. Okay, so that's what we know, right? So now I introduce this notation. So lambda is nothing but the summation part. So first of all, because I'm dealing with exponential function, so the product can be moved inside as summation. So now I break this bracket, so I distribute lambda I into the one, I get lambda, right? So basically I do summation. By our definition, this is lambda, right? So now what I do, I factor out this lambda. Then for the summation part, I will write it as this form, right? So nothing changed, they just a little algebraic manipulation. Now let's define this as PT. So by that definition, we have, right? At this step, it's not difficult to say that this is a probability function of a compound Poisson, right? With n to be the intensity. And this is the PGF of my secondary distribution, right? So I just proved this result, right? So it's just by definition. It's nothing fancy. Finally, we introduced the last way of getting a new distribution. This is called mixture distribution. So basically right now I have n random variables, x1 to xn. Well, they can be discrete, they can be continuous. Okay, it can even be the case that some of them are discrete, some of them are continuous, right? It just can be anything. Okay, denote the corresponding probability function or probability density function by small f. So I construct a new random variable by this particular form. So the new random variable x will be defined using its probability function or probability generating function or a mix of them. So it's defined by this way. So we call this a weighted sum with weight by pi. Okay, those you can think as another probability because they are always between 0 and 1. And when I add up, I get 1. So this is essentially a new probability, right? So another way to think of this construction is I define a new random variable y. In this y can take n different values, okay? It's 1, 2, 3, all the way to n, and the probability of I is pi, okay? That's seen down here. So now what I do, I think, or I somehow imagine there exists a special die. This die has n faces, okay? The value goes from 1 to n. The probability of phase I is exactly pi. So basically, this random variable y corresponds to this rather special die because it can have phases different 6, right? So it can have 10 phases, right? With probabilities p1 all the way to p10. So p1 is the probability of phase 1. P8 will be the probability of phase 8, etc. Okay. So now what I do, I roll this special die. If I get phase 1, I will assign x1 to x. If I get phase 2, I will assign x2 to x. So this is how you can understand the mixture from a different point of view. So the first understanding is nothing but this definition. By the way, you should check this is indeed a probability function or probability density function. For instance, let's just assume all of them are discrete, so they are probability functions. So they are always between 0 and 1, and adding up will be 1. So first of all, it's not difficult to see that it's greater than 0, right? because each component is bigger than 0, and the weight is greater than 0. So it's greater than 0, easy to check. Now I know summing up over the entire sample space, fxi over of x is 1, right? That is because each xi is a random variable, okay? And by definition, if we have a random variable, the summation of its probability function is 1. So now I'm doing summation for this new function, which we don't know yet whether it's a probability function. Okay, I have I from 1 to n, pi times, okay, so I leave this inside. Okay, by this result, each one of them is 1. So it's pi times 1. Okay, by this result, it is also 1. So I just checked. The summation is 1. Then, of course, I can also claim it's less than 1, right? Because it's a non-negative value, the summation is 1. Obviously, it cannot exceed 1 for each small x, right? So I just verified this is indeed a new probability function. Once you have a new probability function, it uniquely defines a new random variable. That's why I call this a way of constructing a random variable, okay? This is nothing but a second interpretation of this result. How about I leave this proof to you, okay? This connects with the previous slide. So here we are talking about a special mixture distribution of x, which is constructed by using weighted sum of n random variables x1 to xn. And this is essentially the result we used before, okay? I give you a quick hint. So y is just what I defined, okay? So y, you can think y as the result of the special die. If I throw this special die and I get result, what is my x? Well, my x must be one of the xi's, right? So if y equals I, then my x is xi. So when I condition, this will be how do I write this? It's this. So let me try how. Okay, so this is essentially what it is. Think about it. Okay, so when my y equals I, my x is xi. So that's why I introduced this indicator. Okay, because we are conditioning on y, and y can be anything from 1 to n. Okay, so it's one of them. So given the value of y, my x will be exactly xi. Okay, and here we know this is when you do the conditional expected value. We know this is I, so this is mu I times y equals I. Okay, then finally this is mu I times, when I get inside, this is nothing but the probability of mu I pi. Okay, you can try something similar to get this result. Theorem 9 is not that important, okay, because it's not common to see this this type of mixture. The last slide is about the continuous mixture. Okay, in this we have discrete mixture because we have n pi's. Each of them is between 0 and 1, and the summation is 1. And how do we move to the continuous counterparty? In this case, we have this result. So h is positive, okay, and the integral from 0 to infinity of this function is 1. This corresponds to pi equals 1. Okay. So now when you do the mixture, you apply this specific function to each one of them. Okay. Here it's you have a Poisson distribution and you want to mixture it. So basically here we are trying to so for a standard Poisson, lambda is a constant. Now you can think a scenario that you don't exactly know the value of this parameter, right? But you roughly know you roughly know the distribution of this parameter, right? So let's say it's more likely to be small values, less likely to be big values. Then you can assign bigger value for this h function when lambda is small, and assign small values when lambda is big, right? So this is how you mix it. Essentially, it's the same idea as conditioning, right? So here you can think lambda is another random variable, okay? And then lambda follows this distribution, okay? Let me conclude this section with one example. I believe from the textbook, we have one example. So I add one page. So that is example 1.12. So if you have textbook, please go to page 1. So it's page 33. So it's page 33 of our textbook. So the claim frequency of a bad driver, for a bad driver, the frequency is PM4. For a good driver, the frequency is PN1. So a bad driver is 4 times likely to get into an accident than a good driver. A town consists of 20% bad drivers, 80% good drivers. What are the mean and variance of the claim frequency of a randomly selected driver from the town? Okay. Of course, this is P1 times N1. So let's call this N1. So the bad guy is N1, good guy is N2. Obviously, this is P1, this is P2. I shouldn't write this because this is another way. So I should write it as probability. So this is what we just studied, right? And since we have the result, so n from 0 to infinity. By the way, this is another way to show why I have that result. So the way I proved is probably more confusing. Here, what I'm writing is easier to understand. So when I write it down, you probably recognize what it is, right? So here I have only 2 mixtures, N1 and 2. You can easily generalize to any number you want. So what is this? This is the expected value of N1. Obviously, this summation is the expected value of N2. So it's 20% times 4 plus 80% times 1. So it's 0.8 plus 0.8 is 1.6. Okay, now we are trying to study the variance. Okay, well, the easiest way is to use my formula, but obviously I hate to ask you to memorize formulas. So let's do this. Again, once you start to write down the definitions, things are not that crazy, right? So what is the definition of n squared? It's simply n squared times the corresponding probability, right? So next, I copy the definition of probability. P1 times Fn1 plus P2 times Fn2. Okay, we already know what we need to do, right? So this time I write things slightly faster. But I do believe you can easily follow why I have this result, right? So what is this? This is variance plus the square of my mean this is the same variance of N2 plus the square of my mean. So it's 20% times 4 plus 4 square plus 80% times 1. Okay, 1. 1 plus 1 square. Okay. So the value is 5.8. So now my variance is this minus 1.6 squared, which is roughly 3.04. So end of this question and also end of this chapter. I have already posted the homework questions. Please work on those homework questions and submit them by the deadline, okay?